My name is John Shonder. The title of the talk is Applying Bayesian Analysis to Measurement and Verification. And if that's not what you are here to see, then you should go to the correct presentation. All right, anyway, I want to go over what I'm going to talk about today. So my agenda here, we're going to talk a little bit about M&V in general, give some background. I really want to sort of set the table, provide a foundation for why I think Bayesian analysis is an interesting topic and worthwhile to us. I'm going to talk about the general problem of calculating uncertainty in measurement and verification, uncertainty of energy savings. I'll give a brief overview of Bayes' theorem and the concept of Bayesian analysis, and then how that Bayesian analysis is applied to M&V. Then we'll talk about some conclusions, some further reading if you're interested, and good stuff like that. So let me tell you a little bit about myself. Currently, my title is Senior Advisor to DOE's Federal Energy Management Program at Oak Ridge National Laboratory. Prior to that, as John said, I was Manager of Federal Business Development for a major ESCO, and one of my responsibilities there was managing their UESC program. UESC, for those of you who don't know, is a contracting vehicle that federal agencies have. They can get performance contracts through their utility. And then the utility in turn hires ESCOs like my former ESCO to do the projects and the measurement and verification, or performance assurance as it's called in UESC. Prior to that, I was Director of Sustainability at DOE, and then for a long, long time, I was a research staff member and program manager actually for FEMP at ORNL. So you can see that year there. I chose the picture that made me look as young as possible while still being relatively recent, but from that date, you can tell I'm not a young pup. But one of the things I did at ORNL was the M&V guidelines that John mentioned. I also was a member of ASHRAE Guideline 14. And my responsibility for that committee was to write the appendix on uncertainty. And it's as I was writing that appendix that I got interested in this whole idea of Bayesian analysis, because it turned out that I found out that I didn't know much about uncertainty. As an M&V practitioner, I had never really been concerned about it or never really got into it. And then I found out that a lot of other people didn't know much about it either. And it seemed to me that Bayesian analysis was the way to go. So I'm going to go into some very basic concepts. I want to set the table for why I think it's important. So, the purpose of measurement and verification. So there's a retrofit project that reduces energy, water demand, and ultimately cost, we hope. And our job as M&V practitioners is to determine the savings that results from that project. We do that by predicting the quantity of energy, water, and demand, or dollars, that would have been consumed in the post-retrofit period had the retrofit not occurred. I'm using this symbol E hat pre to mean the adjusted pre-retrofit energy use, or whatever that quantity of savings is. Now, sometimes, in fact, in most cases, we want to calculate both we want to adjust both the pre and post-retrofit energy use to a typical year at the site. But in this, what I'm going to talk about here is really the simplest concept, where you're just calculating the savings in the post-retrofit year. You're not trying to get a typical year or anything. So we know that this adjusted pre-retrofit energy is an estimate, and we know that there's some uncertainty associated with it. But it turns out that we rarely calculate that uncertainty. So here's an example project. This is a replacement of some gas-fired equipment in a building. We have 1 year of baseline energy on the monthly gas use and monthly heating degree days. And then we have some post-retrofit information as well. So we know that in the first post-retrofit year, the equipment consumed 14,674 units. We want to know how much the project saved. Now we know that we can't just subtract 14,674 from 16,207. We have to adjust that pre-retrofit information, pre-retrofit energy use, to make it compatible with what happened in the post-retrofit year. So we all know how to do this. We just draw a straight line. We use a regression and find a regression equation. Here it is at the top here. So we adjust the energy use this way. We multiply the slope by 3779. That's the total number of heating degree days in that post-retrofit year, plus 12 times the intercept, and we get that, the adjusted energy use for the pre-retrofit year is 17,304. We subtract 14,674, and we find that 2,630 units of natural gas were saved in that first post-retrofit year. So what are some of the error bounds around that savings? We typically use a 95% confidence interval and calculate it that way. So here is what it looks like to calculate the standard error of a simple linear retrofit like that. And so even in the simplest case, calculating that standard error is not simple. This is a matrix equation. I'm not going to go over what each one of these things stands for, but it's something that Excel doesn't do automatically, but you can get it to do it. Excel does, matrix calculation, so you could do this calculation yourself. I haven't seen it done too often. In fact, I haven't seen this equation too often in print. Megami Reddy's book on data analysis contains it, and some papers that he's done in the past, but it's like the ivory-billed woodpecker. You very rarely see it. So once you get that reporting the standard error, you multiply that by the critical values of the T distribution, and that's your 95% confidence interval. So you can say that in this case, the project, say 2,630 plus or minus 1,278 units of natural gas. Now, I don't know whether you think that's whether that range surprises you or not. I mean, that's plus or minus 50%, really. It was a little surprising to me the first time I made that calculation for a project. So even with data that looks fairly smooth like this, there's not a lot of variation in that. We're still going to get plus or minus 50% on the savings. But when we move beyond the simple case, and even for a case like TMY savings, there's really no formula comparable to the one I just showed for savings uncertainty. There are some approximations to that. And even worse, what we're calculating when we calculate that 95% confidence interval is not really savings uncertainty, right? That 95% confidence interval does not mean there's a 95% probability that the parameter lies within that interval. So Bayesian analysis, though, provides a way forward for us to make that calculation. So here's what Bayes' theorem is, and I had to go through this even though I tried to keep it, the mathematics to a minimum in this paper. But basically, what Bayes' theorem says here is that the probability distribution of the parameter that we're interested in, given the data, is equal to the probability of the data given the parameters multiplied by the prior distribution of the parameters, and then divided by this constant of proportionality. Another way of looking at it, since this is a constant, this constant of proportionality, we can kind of ignore that and say then that the posterior distribution for the parameters is equal to the likelihood times the prior distribution for the parameters. And that's pretty much a standard way of saying what Bayes' theorem is. And so you can see that in this case, the parameter that we're looking for is the savings. And so we want to know what's the distribution on the savings given the data, basically. So to compare frequentist versus Bayesian analysis, you may have heard, vaguely be aware that there's been kind of a fight going on in statistics for years and years between the frequentist, which is the one we all learned in college, paradigm, and the Bayesian paradigm. So in the frequentist paradigm, it gives us a point estimate of the parameters of interest. So the slope, let's say, and the intercept. We get and then a 95% confidence interval means, and this is kind of a mouthful, but I'm going to say it, that if we were to repeat that measurement process over and over again and calculated 95% confidence intervals, The true parameter would be within the calculated intervals 95% of the time. Now, if we are calculating something like the average height of males in the US population, then we can consider that we would do that over and over again. So let's say we've got a sample of 100, and we could calculate what our 95% confidence interval would be. We can certainly imagine picking a different set of 100 men, let's say, and calculating different confidence intervals and a different mean. And what that means basically is that we would 95% of the time, our mean that we calculated would be within the 95% confidence interval that we calculated given that data. But for our purposes, when we're looking at a retrofit project, it's a little conceptually difficult to imagine us going back to the pre-retrofit year 100 different times and calculating that over and over again. So right away, that 95% confidence interval doesn't make a lot of sense in our field. Okay, so Bayesian analysis does produce probability distributions for the parameters of interest, and with those probability distributions, then we can say that there's a 95% probability that the mean, let's say, of the parameter lies within a given interval. So in other words, the meaning of uncertainty when you use Bayesian analysis does correspond to our intuition. So I like to title this slide, "Don't Panic," because for most simple problems, that includes this simple linear case, Bayesian analysis is going to give you the same answer that you would get with a frequentist approach. So the same mean values of the regression parameters, that's the slope and the intercept, the same value of the savings, and the same value for the savings uncertainty. So here's how you do this in the Bayesian framework. So you write down the joint posterior distribution function for, and beta, I'm using this as a vector here for the vector of the slope and intercept, and then sigma is the standard deviation then of the data. So you write that down, you translate that into a language, and you put that into a standard software package. That software package draws thousands and thousands of samples from that distribution using something called Markov chain Monte Carlo, or MCMC. So you're going to draw from this distribution. Each sample is going to give you a distinct value of slope, intercept, and standard deviation. And with that, you're going to be able to calculate a new value of adjusted pre-retrofit energy use. You'll subtract that from the post-retrofit energy use, and that gives you a value of the savings. And then you do that thousands of times, you'll get thousands and thousands of different values for this savings, and that gives you a distribution. And then from that distribution, you can calculate means, you can calculate confidence intervals, really anything you want about that distribution. So you were getting ahead of me here, but what do I mean by that joint probability distribution? It looks something like this, okay? So it's strange because it's a four-dimensional object, okay? So unfortunately, I can only show you a three-dimensional object, but you have to imagine that there's another dimension that involves sigma here, this standard deviation. But basically, what it means is that certain of these slopes and intercepts are more likely than others, and when we draw from this distribution, we're more likely to draw from the center of it, where most of the probability mass is, but we will occasionally draw from values out at the edges, okay? And it's the same with the standard deviation as well. So this equation here that looks a little bit complicated is something that actually you've seen before. You may not know it, but you use it all the time. So on the right-hand side here, after the pi, that's just the likelihood of the data, or the likelihood of the data. So every time you do a linear regression, you minimize this equation to find the parameters that correspond to the minimum value of the likelihood, or actually the maximum. I'm sorry, the maximum value of the likelihood. And then this here is the prior distribution of beta. So that's this basically the vector that defines the slope and the intercept, and this is the prior distribution on the standard deviation. Actually, the standard deviation is squared, so that's the variance. So again, we use a specialized language to specify that distribution. We use specialized software. That software is open source. It's available for free. There are a couple of different packages. There's something called WinBugs, another one called JAGS, just another Gibbs sampler, a couple of different ones. They're all available for free. And then what we do basically is draw from that distribution. And I'm going to show you on the next slide here. So every time we draw a sample from that distribution, we get a different line. And you can see that, you know, this is an ensemble of those lines. And basically what this means is that these are all possible lines that could have given rise to that data, the data that we've collected in the pre-retrofit period. Now, there's also a standard deviation associated with each one of these lines because we selected a sample that gives us a slope, an intercept, and a standard deviation. I can't show that on this figure, unfortunately. But you'll notice that most of the lines are bunched up basically where we would expect. You know, if we were to draw that regression line by eye, we draw it down the center basically, and that's where most of those lines are lining up. But there are a couple way out here, you know, so there's a small chance that a strange line like this could have generated the data, but it's pretty small. So now let's see what we do. So for every one of those lines, we do this calculation. So let's consider one of these lines, just the ones that I've highlighted in red here. That corresponds to this equation here. So 500 plus 2.9529 times the heating degree days. And it has a certain standard deviation associated with it as well. So we're going to calculate E pre-adjusted. So we're going to take 12 times the intercept, and we're going to take 2.9529 times the total number of heating degree days in the post-retrofit period. And we're also going to add 12 standard normal variables that have a mean of 0 and a standard deviation of 103.6. And that's going to give us a possible value for the adjusted pre-retrofit energy use. So that's a value that we could see in the post-retrofit year had we never done the retrofit project. So that gives us 17,382 units. We subtract the actual gas use that we saw in the post-retrofit period, and that gives us a savings here of 2,708 units. So from each one of these lines, we're going to do that calculation. And we're going to get thousands and thousands of different values for the energy savings. And with that collection of values, we can generate a distribution. And in this case, here's what that distribution looks like. So, you know, most of the values are around 2,700. And in fact, the mean turns out to be 2,630 units. That's exactly what we found from our other analysis, from our classical analysis. And when we look at, you know, the 95% credible interval, so in other words, the 95% of these values that are centered around that mean, we get the exact same value for the confidence interval as we got with the classical method. So 2,630 plus or minus 1,278. So that's what I mean when I say that for simple linear problems, where a classical solution exists, we know we're going to get the same answer, whether we use classical analysis or Bayesian analysis. You know, but in order to do that, we had to assume non-informative prior distributions for the regression parameters. So we assumed essentially flat priors. We don't always have to do that. If we have some good information on what the regression parameters are before we do the experiment, we can certainly use those as long as we're justified in doing that. Another thing is that the Bayesian result is probabilistic, but we took enough samples to show that it converges to the classical result. Now, the thing is, we knew the classical result, so essentially we kept drawing samples until we got to that classical result. The problem is, what if there is no classical result? Then how do you know how many samples to take? And how do you know when you're getting close? Well, you don't, right? So that's why we have to use Bayesian inference is in these more complicated problems. Okay. So as I said, we can get the same result if there's a classical result that exists, but a classical result does not exist in all cases. And as I said, even for the simple case where we're calculating TMY savings, there's no classical exact result for that. So you have to go to a Bayesian. There are some approximations, but how do you know how good approximation it is when there's no real answer? So the only way to do that is to compare it to a Bayesian analysis. So here's a much more complicated problem, but this is a typical real problem that we deal with in M&B, right? So this is a project that we did at Oak Ridge National, or an analysis, let's say, that we did at Oak Ridge National Lab many years ago. It was a ground source heat pump project. They replaced air source heat pumps with ground source heat pumps. The classical way to analyze this problem is to fit that data. This is daily data, so each one of these points is a day. That's the daily energy use versus daily average temperature. You fit that to something called the breakpoint linear 5-parameter model. And even though it's got the word linear in it, it's not linear because it's 3 different lines basically. And in this case, you wanted to calculate the TMY savings and the uncertainty. So that's a nonlinear problem. And it turned out also that the residuals of this project, of this data, were not random either. So I'm going to take a look at the residuals now. So these residuals exhibit serial autocorrelation. What that means is that when you fit the data to the regression line or to the regression curve or whatever you want to call it, days where the energy use deviates significantly from that line are going to tend to be followed by other days that deviate significantly from that line. So we're looking at the lag 1 residuals, and vice versa. When there's a day where the energy use is significantly below that line, the following day is also going to be significantly below that line. So that's what we mean by serial autocorrelation. Now, there are ways to calculate the uncertainty, believe it or not. So that problem is important enough that people have come up with a number of approximations in order to make a frequentist calculation of savings uncertainty. But you have to do a lot of things. You have to, first of all, ignore the uncertainty of those breakpoint temperatures. So, it looks to me like that's pretty uncertain, right? So we don't really know what that temperature is. I mean, we're converging to a value for that temperature, but that, seems to me that there's a lot of uncertainty in that temperature, especially even look at the post retrofit. There's even more uncertainty in where that breakpoint is. But you ignore that uncertainty of the breakpoint temperatures. There's also a heuristic fix for the autocorrelation. So you sort of like heuristically reduce the number of points based on what the R squared is for that lag 1 plot there. And then also you have to ignore the correlation between the pre and post retrofit TMY savings. So, you can do all that, but the question is, how do you know how close you are to the right answer? So I wrote a paper about 10 years ago, we showed all of this. We did the classical calculation, and we also used Bayesian analysis and found that, the error bars, or let's say the uncertainty, was considerably wider than you would get using this frequentist method. I think we also got a sort of slightly lower answer for the savings as well. And is that answer right? Well, we don't know, right? Because we don't know what the real answer is. Okay, I think you just have to do that many times, and we need more experience with that technique. So let's see. So I guess now we'll get to some conclusions here. So, where the analytical results are available for savings and savings uncertainty, you can reproduce them to any degree of accuracy using Bayesian inference, as long as you take non-informative priors on all the parameters, and as long as you take enough samples to make sure that the data is converging to the same answer, okay? But Bayesian inference solves problems that can't be solved using classical techniques. And, you know, one of the simplest ones is, you know, even a linear pre and post retrofit problem where you're trying to calculate TMY savings. We did that in our paper. We compared the Bayesian analysis to the approximate result for the TMY linear problem. Found that it was pretty close, at least for the problem that we examined, but that's not to say that it'll be close for other problems. And you know, you really don't know because it's just an approximation. But when you look at a bit more complicated problems, then the comparison of the Bayesian results with the approximate results suggests that the approximation is not that accurate. Okay, so the answer that we got for that, you know, a little bit more complicated 5-parameter model was not as accurate as or did not correspond to the approximate classical result. Also like to mention that Bayesian inference is widely used in other scientific fields, like pharmacology, like medicine. You know, these are fields that have life or death consequences, and if they're good enough there, I don't see any reason why we couldn't use them in our field. And then, you know, Bayesian inference is very useful for calculation of savings and saving uncertainty, and I think it has a lot more applications in M&V than just that. And on the next slide, I want to talk about some of those other potential applications. So, you know, we never really, you know, when we calculate savings uncertainty, we're really only usually talking about the uncertainty of the costs of the energy savings. And when we do a project that involves electrical savings, oftentimes the tariffs that are used for electricity, or, you know, the electrical rates, are very, very complicated and very, very nonlinear. And we never really calculate the uncertainty in our dollar savings. So it would be possible using Bayesian techniques if you could reconstruct the year, you know, the daily electrical use, or maybe even the hourly electrical use, and run that through the actual tariff. You could, you know, you could do this 1,000 times or 10,000 times and calculate the savings, the actual savings based on that very complicated tariff, and then calculate the uncertainty in the dollar savings. Nobody ever does that calculation that I've seen. You can also use something called Bayes factors to assess model fits. So another thing too is, you know, option D is one of the techniques that's sort of sanctioned both by the IPMVP and by FEMP and by ASHRAE guideline 14 as well. But there's really no way to assess, you know, how good of a fit that model is. So as compared to other ones. So you could use this technique called Bayes factors to, you know, tell you whether your option D model is a good model or not. There's something else called hierarchical models, and this takes a little bit of explaining. But let's say you have a number of different schools in a school district, and you've done retrofit projects in each one of, say, 10 different schools. You can analyze each one of those schools separately to find what the savings is for that particular school. But when you have a hierarchical model, you assume that, for example, the savings, that there's some, let's call it hyper savings, that there's some type of a normal distribution that the savings revolves around for all those different schools. And then you can combine all those schools together and calculate what's the distribution all together of the entire school district, and then use that to get more accurate measures of the savings of the individual schools. Finally, I also wanted to mention sample size calculations. So there's, you know, you look at the IPMVP, there's a way to calculate the sample size, let's say for a retrofit of a lighting measure where you've done thousands and thousands of lighting retrofits. So you go back afterwards and you select a sample of those and measure the KW draw of the fixture. the funny thing about that sample size calculation is that we're supposed to know the standard deviation of the voltage of those fixtures in advance before we even do that, in order to calculate the sample size. You could do a Bayesian analysis of that, where you might, draw samples and then it would tell you when to stop, right? So you may be able to take fewer samples than you would normally calculate, where you're assuming what the standard deviation is already. So that's another place I think that Bayesian analysis could help. Let's see. So I wanted to talk too about some further reading if folks are interested in this topic. So there's a very good book that's not mathematical at all. It's for a general audience. It's called The Theory That Would Not Die, and it's all about Bayesian analysis and how it's been used through history, basically since the 1700s, when it was first thought up by Thomas Bayes. It's been used during the war. It's been used to break German codes during World War II. It's been used to locate submarines during the Cold War. And as I said, it's used in drug trials and things like that. And so this lady wrote a very, very interesting book, at least for me, back in 2011. If you're interested in the mathematics behind it, this book, Bayesian Data Analysis by Gelman, Carlin, Stern, and Rubin, is really kind of like the gold standard. It's the most basic text. That's 2013, I think, was the second edition. A much simpler book that I really like was Bayesian Computation with R by Jim Albert. Jim is a professor emeritus at Bowling Green University, and he is a baseball expert, so he does a lot of examples using baseball statistics, and it's easy to learn Bayesian techniques that way. Steve Cromer turned me on to this book called Statistical Rethinking by a gentleman named Richard McElreath. I believe he's a professor too. He also has an interesting YouTube channel where he has lectures recorded that it's kind of like supplemental material to his book, and that's a very interesting YouTube series. Finally, I want to mention our paper, this paper that we did in ASHRAE now more than 10 years ago, but Bayesian analysis of savings from retrofit projects by myself and my colleague Pil J. Im, and there's a reference for that. So I think we, maybe I'm a couple of minutes early, but I think we have quite a bit of time left for questions. So I will turn it over to John if you'd like to ask any questions, and then maybe turn it over to the audience.
Okay. Oh yeah, camera. Yeah, that was full. I mean, that was so full of information. I feel like
too much.
well, no, you can't teach it in 45 minutes. I don't think you can do it. But it seems like it's something. Well, just tell me this: is this something that we put out this software, this Option C software? Is that something we could actually integrate into the software? That's something we could do if they just had 12 bills, correct?
Yes, you could.
That's what I thought. Yeah, you just do it with a bunch of different balance points, or maybe deselect a point here or there.
Yeah, I mean, you could, if I wanted to go back to the, you could, I don't know, I'm not familiar with your software, John. We had it at the ESCO I worked at, but I did not work in the M&V department, but your software could certainly incorporate this equation. Mm-hmm. Not that complicated. It looks complicated, but it's just a matrix equation.
It's math.
And you calculate you could calculate the uncertainty.
Yeah, that sounds really fascinating. Okay, I'm going to read a few comments and questions from some of the folks. So here's one. It said, it seems to me the real problem with post-retrofit M&V results lagging expected results is that ESCOs routinely overstate projected savings up front. Perhaps ESCOs should be using these more advanced methods to develop the original savings estimates.
Yes. I mean, that's kind of a hard question to answer. I mean, first of all, let's look at a project like this one. how would you calculate? I mean, until you know what that's going to look like, all you can really use is your own experience on previous projects to estimate the savings there. I mean, I give ESCOs a lot of credit. So to be able to, sign a contract that says you're going to, before this goes into the ground, right? To say that you're going to deliver that amount of savings every year, that takes a lot of experience and a lot of faith, because I think there's a lot of risk in that calculation. So
Yeah.
could there be, are there advantages? Yes, I think there are advantages to using a Bayesian, because I think the Bayesian analysis could tell you, for example, how much variation could you expect to see from year to year, and how much variation could you expect to see day to day. So
Could you use it though in DO2 models or eQuest models or trace models, something like that, where it's like, well, we guessed on what the watts per square foot of lighting was. Maybe it's not, 0.8, it's 0.81. No, maybe it's 0.82. Maybe the CFM really is this and not that. The outside air maybe is this and not that. Couldn't you use it for that?
yes. So in other words, let's go back to a slide that I put up here. So when I showed, in this case, how I was calculating, given a line, how I calculated what the savings was for that specific line. So you could, for example, go out and recalculate the savings. You could call, let's say, given a value that you calculate here, you could go back and rerun your model. Okay, you could rerun your Energy Plus model or your eQuest model. Certainly, it would take a little while, but you could do it.
Okay. Let's see. Oh, and one other thing about that question, or your comments and that question is, there's a lot of uncertainty involved in the construction and in the customer's behavior after everything's put in. And how do you estimate that? I mean, you could, let's say that you are able to use models and know your uncertainty and do the whole Bayesian thing on your DO2 model. But so what? Your guys might install it wrong. So what good is that? So
yeah,
just a quick comment. Okay, so this was a comment. Now I'm not sure where this came in. So it came in early, so you might know. Someone asked, can you talk about how you get the distributions for beta initially?
Yeah. Okay. So there are standard. I mean, what I used were non-informative distributions. Okay, and there are, I mean, for the slope, that's really just a straight line, basically. But you do know more about the slope than you think, right? I mean, it's going to be positive, right? So you could use a distribution, a prior distribution that says we're only to consider values, say, between 0 and whatever you think, 10, whatever is a reasonable value for that slope. So I would say, that's one way you could get the prior distributions. You could say, well, we don't know what the slope is going to be, but we know it's going to be positive, and we know it's going to be somewhere between 0 and 10. Whatever value makes sense makes the most sense. I think for the standard deviation, you don't want to use a straight line. That parameter you definitely know is going to be positive. The standard distribution is always positive. And I think there's a standard type of prior that's used for that. It's all in the literature. I mean, that book that I mentioned, Gelman and Carlin, that's where you learn about that kind of stuff. So it's mathematical.
Okay, here's another one. How do you determine the duration of your pre-retrofit period?
Well, that's an interesting question. I mean, most people only go for a year. That's pretty standard. But I think if you, so here's our data. So, but I think, if you were to use more than that, then I think that uncertainty would go down, right?
Even if the building changes, though, in the middle of the year?
Yeah, that's always a possibility too, right? But let's say you had 2 years of pre-retrofit data, you would certainly get a lower savings uncertainty than if you use just 1 year's.
Assuming the building is identical at the beginning and the end.
It's the same.
Yeah.
which rarely ever happens, right?
That's
I mean,
right.
we know that there are changes. Things happen like COVID, completely unexpected, right? So.
That's right. How can we use Bayes for doing M&V planning or simulating uncertainty? Or no, simulating uncertainty, is that maybe, I don't know. I don't know what that part means, but how can you use it for M&V planning?
Let's see. Well, I think you would, ESCOs will certainly have some idea of what they've seen in the past, the type of variation that they've seen on the savings in the past. So they could build a model like this, and a simulation model, and then run that thousands and thousands of times and see what the variation that they get in the savings is. I mean, I think that if there's a lot of variation, then they should perhaps plan for that, right? And plan to be able to explain to their customers why that variation exists, and how to control for it.
Okay, here's another one. Why should we use non-informative priors, and what happens if we don't? And can you, before you even answer it, can you, I guess, redefine or define what is a non-informative prior?
Okay, that's a good question. Now, one of the criticisms of Bayesian statistics over the years has been, my prior might not be your prior, John. So let's say I think that this parameter is, has a value of 1, and so I'm going to use a prior that's centered around 1 and has a very narrow distribution. You, on the other hand, have a different idea. You think it's closer to 5, but you think it has a wider variation, and so your prior is different from mine, right? And so the criticism that people have, and that would give a different answer, right? Potentially.
Right.
So in order to get around that, people said, well, let's use priors that are non-informative. So let's not assume anything up front. Okay, so we're not going to say that the value of the parameter is 5, or we're not going to say that it's 1. We're going to say that it's flat, basically. So we don't know anything about that parameter. So it could take on any value between 0 and 100, let's say. So that's what we mean by non-informative. And that's really a way to get around that criticism.
Okay.
But I do want to say this, though, that no matter what, if there's a lot of data, and especially in that case of the 5-parameter distribution that I showed, there were 365 data points. It really doesn't matter what your prior distribution is, because it's going to be swamped by the data. Okay, so I think that whole question of which prior to use is a lot more important if you have a very small number of data points. If you have a large number of data points, then the data is going to dominate. Okay, not the prior. So,
okay.
I don't know if I answered the question.
Thanks a lot for answering or asking all these questions. That's great. You guys are asking great questions here. Here's one. Is the Bayesian method used in analyzing multi-factor indoor environmental data before and after renovations or changes?
I can't answer that. I mean, just from the perspective of the ESCO that I work for, and I'm sure that's typical of many ESCOs, and even from the perspective of people who wrote Guideline 14, I would have to say no. I don't think Bayes is used much in M&V at all. And the reason I say that is because I went out and did a web search on Google Scholar, and I just searched on the terms M&V and Bayesian analysis. You find about 10 papers out there. There's a guy in South Africa who seems to be a very much a proponent of this technique. But besides him, you don't see a lot of work in this area. You don't see a lot of papers. So if it's being used, they're not publishing. That's all I can say.
Okay, I got, so Bill has given us a couple references. It says for a detailed layperson's comparison of uncertainty method. So this would be, and Bayesian is part of it. I'm sending this, so I don't know if you'll be able to see it in your go-to webinar.
Is this Bill's? Is this the report that Bill wrote? I was looking for that and couldn't find it through a web search. So
it may, I'm not sure, but anyway, so I just sent it to everyone. So I hope you guys can see it. And I don't know how to tell you where to see it, but it's somewhere on there. We just, I just posted it sent it to everyone. So it's under messages, I think, or something like that.
okay.
Thanks, Bill. Okay, here's one. How do customers react to estimates of savings that include uncertainty? Yeah, that's a really good question.
Good question for you, John.
I think he's talking about ESCO customers, and you know, you worked for an ESCO, but I know you weren't doing M&V. But I mean, I don't think you guys were giving uncertainty at your ESCO, were you? And have you heard of?
I mean, you know, and that's one of the reasons why this is not done, is because customers don't demand it. Okay,
Right.
Customers don't ask for it. But you know, customers do have preconceived notions about M&V, and I'm not going to, you know, mention anybody in particular, but a lot of people think that option C is like the gold standard, right? Because it's the utility bills, it's what you're paying, right? And we've seen from this calculation, I mean, you know, the precision of the savings, at least in this project, was plus or minus 50%, right? So
I'd sure like to hear what Bill has to say about that. But I don't think we'll be able to get him on.
I'd like to hear a webinar from Bill.
Me too, but I don't think he's going to do it. Just so you know, we're talking about Bill Coran, and Bill's retired, so he's busy doing funner things.
Bill and I worked on guideline 14 together, so I know Bill pretty well.
Okay, here's another one. Can you talk about how you get the distributions for beta initially?
Yeah, I think we just kind of answered that question.
Okay.
Yeah, the beta was the slope and intercept.
Oh, that's right. I think okay. Let me see what this one says. Okay. Now this says, do you think these are the best techniques to be able to say, for example, you have a 90%? Okay, right. So if you, in some of those, I think ASHRAE, maybe ASHRAE, but I think EVO's, in some of these documents, I'm all confused. I'm on vacation, guys, so I don't remember anything. But, you know, something says, you're supposed to say, I guess, you have a 90% probability of achieving at least 85% of this estimated number that I gave you, you know, so. And the question is this how you would get those numbers, that, you know, the probability and within 85%? Does that make sense, what I'm asking, John?
I think what you're thinking of there, John, is like when you take a sample of, let's say, lighting fixtures, your goal is to get a 90-10 sample.
Right.
To be an 85-10 sample. And what that means is, you know, you want to have at the 95% or 90% confidence interval, you want to be able to measure that parameter plus or minus 10%.
Well, it's not that. So I don't remember which one, but I think it's in one of the EVO's docs, and it says something like, look, when you're presenting M&V, you should also present an estimate of uncertainty as well. And so you don't just say, look, you saved a million kilowatt hours. You say you saved, well, I'm 90% confident you saved, or, you know, you saved a million, or at least 85% of, give or take 15% of a million, something like that. And the question was, can you use this Bayesian analysis to fill in the numbers in that sentence? And
I would say
you save within this amount.
Yeah, and I would say yes, you can. And as a matter of fact, you know, if you're using, as I said at the beginning, if you're using classical statistical techniques to calculate a 95% confidence interval, then you're not really giving a 95. Then you're not telling me that the savings is within those bounds. That's not the meaning of that 95% confidence interval. Now we've shown that for a simple linear case, it corresponds to the same thing, right? It means that, it means the same thing as it does in the Bayesian sense. But when we have more complicated projects like that 5-parameter one, then we don't really know whether it's the same as the Bayesian confidence interval or not, do we? So I would say that Bayes would give you a better estimate of than classical techniques.
Okay, I think we're almost there. So I ran out of questions. Do you want to give us a last word, John, before Tyler jumps in and tells us about the webinars that are coming?
Okay, I do want to give a last word. So I was reading your paper recently, John, this paper that you published about savings uncertainty. And I think you were right. I think that these, may have more of an application in utility types of analyses. And just as a citizen of the planet, if I would hope that if we're going to do something that reduces carbon emissions from our, we're going to do some project that's designed to reduce carbon emissions, I would hope we'd be doing that, in the most accurate way possible, and that we'd know. So let's say this bill is going to reduce carbon emissions by 10% or something like that. I'd want to know what's the error bound on that, right? So is this project really going to save? Really going to reduce carbon emissions, or is it just a feel-good measure, right? I mean, I think it's that important for us, right?
Well, also, I mean, that's the difference between, I think, utility and ESCO. ESCO is one client, and okay, sometimes they're big jobs. It's 5 million, maybe. If it's the military, maybe 20 million. But with utility,
I would say much larger.
Yeah, they're dealing with billions of dollars in California, or at least, maybe a program might have, tens or 20, hundreds of millions of dollars. So when you have bigger sums of money, I guess you do want to know, how certain are you that you're really going to get the savings? And if the government's doing a bill, then we're talking trillions of dollars or hundreds of billions. And then, yeah, certainty, the bigger the number is, the more important certainty is. I think that's probably what you're saying.
And plus, when we talk about climate change, I think there's nothing more important. I think it's, forget the dollars. We're talking about, our children's and our grandchildren's lives. So we definitely want to be certain that we're doing the right thing.
But then
that's all I'll say.
You can bring the certainty into the modeling too, though, I guess, right? The climate modeling and their certainty. But let's put that aside. That's it, everyone. Thanks for coming. Appreciate it.